Alright, welcome to AP video 10.1. This one's on intermolecular forces, or IMFs. Like you'll be able to compare and contrast the different types of IMFs, London dispersion forces, dipole-dipole, and hydrogen bonding. And then number 2 is going to be kind of an overarching objective you'll see in many of the videos. Be able to use IMFs to maybe explain some of the properties of liquids and solids, why things are solid and liquid, and some of the properties that those two states of matter have. Alright, so in this chapter, we're going to consider some of the properties of the condensed states of matter, like solids and liquids. And some of those properties that we're going to investigate, they're the result of two major forces we'll look upon on the next page. So one of the major forces that impact states of matter and properties of solids and liquids is the thing called an intramolecular force. Intramolecular forces are the forces within a molecule that hold the atoms together. So if you take a look at this picture here of water, these are the intramolecular forces that hold the atoms together to form this collection here that we call a molecule. So basically we're talking about chemical bonds when you say an intramolecular force. The word molecule basically implies we're only using covalent bonding, but an ionic bond, if you look at ionic compounds, ionic bonds are also considered an intramolecular force because they hold the atoms together. But intramolecular forces are a fancy way for saying chemical bond. And intramolecular force in terms of energy, they usually take quite a bit. They take about 140 kilojoules per mole to break a bond. They might take a lot more. They might even take up in like the 400s, 900s, maybe even the 1000s. So usually more. But intramolecular forces, because they require so much energy to break them, that indicates that bonds are always strong. Okay. On the flip side, we have the intermolecular force, also called an IMF. And inter means between. It's the force between molecules which holds the molecules together. So if you look at my little picture down here, here's a bunch of water molecules, and I use a dashed line between them. This dashed line here represents the intermolecular force, the force between the water molecules that holds them together. Intermolecular forces usually require between 2 to 40 kilojoules per mole. So at most, they're 3 times weaker than a chemical bond. But basically that shows they are weaker. Intermolecular forces don't take as much energy to break, and they are weak. Up next, I want you to write this along the bottom of your page here. Molecules are covalently bonded together. So here's a molecule covalently holding the atoms together. But intermolecular forces hold molecules together. So write that little statement down at the very bottom of your page underneath this picture that you have in your notes. And I like this picture back to back because it really shows the idea that a chemical bond is inside of the molecule. So an intramolecular force is within, and intermolecular forces are between the molecules. And it turns out, as we analyze solids and liquids and some of their properties, you have to be thinking about, is this a result of an intramolecular force, or is this the result of an intermolecular force? Okay, up next we're going to go through the different types of intermolecular forces. You need to know these like the back of your hand. You need to know what a London dispersion force is, a dipole-dipole, and a hydrogen bond is, and understand when they take place and what their potential causes are on other properties. So let's start with the London dispersion force, also called an LDF. It's named after a chemist, London. London dispersion forces is an idea that a temporary dipole force is caused by the random movement of electrons. Remember, a dipole is when you have an asymmetrical distribution of electrons. It's a fancy word for saying the molecule is polar. So dipole means that the molecule is polar. Okay, so here we have two nonpolar molecules, and electrons are always moving around in this nonpolar molecule. And if you were to say pause and look at this nonpolar molecule, it's possible they might at a given instant be more on this side of the molecule than this side of the molecule. So what you've created is a temporary dipole, because as soon as you say unpause, the electrons are going to go back to being, on average, symmetrically distributed and nonpolar. So a molecule can go from nonpolar to polar at any given instant, kind of like this, because of the random movement of electrons. And if they randomly move asymmetrically, you create a dipole. Then what happens is this dipole here, this partial positive part of the molecule, kind of causes the electrons in a neighboring molecule to get pulled to this side of the molecule, and the molecule becomes temporarily polar. And now that you have two temporary dipoles, because of the random movement of electrons, they can attract to each other temporarily. So this attraction here is temporary, because as soon as one of them goes back to looking like this, they stop attracting. Okay? So molecules switch back and forth like this all the time, and they temporarily attract to each other based on this. And that is the reason why these LDFs are the weakest of the IMFs. It's not a permanent force of attraction between molecules, it's a temporary attraction. That's what makes it a weak force. When we talk about nonpolar molecules, this is the major force of attraction, holds nonpolar things together. So LDFs are definitely between nonpolar molecules, and they're also between noble gases. Remember, noble gases are just atoms, and they don't bond anybody. And if an atom of helium comes in contact with another atom of helium, what possible attraction might those two things have with each other? The only possible attraction is a London dispersion force, based on the random movement of electrons creating temporary dipoles. I guess the big take-home picture here is, notice as the noble gas becomes bigger atomic number, more electrons. Yes, the mass gets bigger, but notice as it gets bigger, the melting point becomes higher. The boiling point becomes higher. And here's the big idea. When you increase the number of electrons, that makes the molecule more polarizable. What that means is the ability to form those temporary dipoles. So the more electrons an atom has, I'm going to go back a page, the more electrons an atom has, the more likely it's going to do what this molecule on the right here is doing. It's going to go from being nonpolar to polar to nonpolar to polar. The more electrons an atom has, or a molecule has for that matter, the more likely it's going to create those temporary dipoles. And when you have temporary dipoles, that causes attraction. So that's why you're seeing higher melting points as these atoms get bigger and have more electrons. Okay, up next we have the dipole-dipole force. A dipole-dipole force, key word here is permanent. It's a permanent dipole in polar molecules that attracts together. So take a look at my picture here. Here's the big difference. Both of these molecules are permanently partially negative and partially positive all the time. So when these two molecules come together, they can attract all the time. This dipole is not going to go away. So there's always attraction between opposite partial charges there. And this one is considered to be the medium strength of the IMFs. And a really good example for this one would be hydrogen chloride. HCl bonded together here. The chlorine pole is harder, so the electrons spend more time over here and make this part of the molecule partially negative. Hydrogen is left partially positive. And when a neighboring hydrogen chloride molecule comes in contact with it, these parts here can attract to each other because of that permanent dipole between the two. The next type of intermolecular force is called the hydrogen bond, and it's important to know that this is not a bond. That's very misleading. Okay, not a bond. It's still an attraction between two molecules. The hydrogen bond, I think the reason they probably call it a bond is because it's unusually strong for an intermolecular force, but it's not a bond. So it's still it's a type of dipole-dipole that you just saw on the previous page, a permanent dipole between molecules attract together, but it's unusually strong. And the hydrogen bond is the strongest type of the IMFs. The reason that this is unusually strong is because somewhere in the molecule, hydrogen is bonded to X, whereas X is either nitrogen, oxygen, or fluorine. So let me give you a quick example here. I guess we'll just do water. Okay, so in this molecule of water, somewhere in the molecule of water, hydrogen is bonded to X, where X is either nitrogen, oxygen, or fluorine. And what happens between those two, there's unequal sharing of electrons. And it turns out oxygen is partially negative, hydrogen is partially positive. Because of the unequal sharing, oxygen is more electronegative. And what you have here now is a large difference in electronegativity, and this creates a very polar molecule. So here's the picture from the previous page. If I were to show a bond between oxygen, and hydrogen, rather than being partially positive, it's really, really partially positive. And over here it's really, really partially negative. So the difference between these two is much larger now. And what I like to kind of compare this to is that this is like a really, really strong magnet, really strong poles, whereas in the temporary, on the previous page, these are partially negative and partially positive. You know, they have a difference in electronegativity, it's unequal sharing. However, in hydrogen bonding, it's a very big difference between the two. So this is like a stronger magnet type example. So when another molecule is very partially negative and partially positive, this attraction here is even stronger than it is on the previous example. So somewhere in the molecule, and this molecule can be huge, it can be a big molecule, really complex. Somewhere in there, if hydrogen is bonded to any of those three elements, that creates a very strong dipole in that bond. And if it comes in contact with a molecule who also has that going on, they attract together very, very strong. Okay, so the hydrogen bond is the strongest of all of them. And we'll practice one in class because it's kind of a tricky one.